Okay, hello everyone. So I'm going to do some more video lessons. In this one, I'm going to do a few from the workshops. So from lab 3, I'm going to do the last two questions. So question 10 and question 11, in which question 10 is this one about converting binary to decimal. That is, yes. So binary to decimal. And question 11 is the computing the pi to a certain amount of accuracy one. So I'll just call those pi. From lab 4, I'm then going to be doing questions 4, question 8, and question 10. Okay, so from those, workshop 4, question number 4 is the perfect number, so perfect number 1. Question 8 is the Goldbach conjecture, I think that's the word. Goldbach conjecture. And then number 10 is converting from decimal to binary. So decimal to binary. Okay, so yeah, let me go through these then. So starting off with question 3, in workshop 3, it is to convert a number from question 3? Question 10, sorry, in workshop 3. So convert a number from binary to its decimal equivalent. So in this case, let me create this. And as usual, I will put all this up on my GitHub, so it can be accessed at github.com/Luke611, and then in repositories, and then in 1806 ICT. So I'll be putting all the code here to have access to. So the first one I'm going to call lab 3 question 10 here. So I will create this file. lab3.q10.c. Okay, so GCC lab 3, include that, and run. Okay, so we've got our number, which is going to be our binary number. So let's start just with this basic one here. B equals this, and then we want to convert it to our decimal output. So technically we're starting off with this B, which is an integer, but it just happens to encode our binary digit. So let's start by going in a for loop that's starting at I, and it's going to go for n times. So n in my case is going to be log of B divided by log 10. In which case, actually, there's just a log 10 function, I think, that does log to the base 10, and that will be +1. So that n is going to tell me how many digits, so it should return 1, 2, 3, 4, 5. So here I'll just print out for testing this binary number, actually, binary number this has this many digits. Okay, So this has n many digits. So I'll test that out. Let me put clear for each. So this one has 5 digits. So 1, 2, 3, 4, 5. So that's correct. So then let me go up. I starting at 0, so I don't need to put anything in there. Whilst I is less than n, I++. And here we're just going to get each digit. So I will get b divided by 10 to the power of I, and then I will mod by 10. And let's print out each digit here, d. So I'll test that, and then this should be this backwards, so 0, 1, 0, 0, 1, 0, 1, 0, 0, 1. Okay, so we're getting out each digit. Now what we need to do is actually, we know that this is the 1's place in binary, this is the 2's place, this is the 4's place, this is the 8's place, and this is the 16's place. So here we actually need to, let's have a result, so let's call it d and set it to 0. And then I will create a factor that we're going to multiply this digit by in order to add the correct number. So let's put this as, it's going to be 2 to the power of I. So instead of using base 10, we're assuming that this is in base 2, so in binary. So let me get this value, and I'll say digit I is 2 to the, I'll say it's in this column, so is in the column. Okay, and then I have that digit is in the F's column. Okay, so then let's test this out. So digit 0 is in the 1's column, digit 1 is in the 2's column, digit 0 is in the 4's column, digit 0 is in the 8's column, and digit 1 is in the 16's column. So all I need to do is add these. So 0 times 1 is 0, plus 1 times 2 is 2, plus 0 times 4 is still equal to, plus 0 times 8 is still equal to, plus 1 times 16, so 16 plus 2 is 18, and if we look back at this, that is the correct answer. So then let's put our digit and set it to be digit plus f times d. Then we can print out, should be able to print out this in binary is this in decimal. Actually, even we can just this in base 2 is this in base 10. So b and then d. Then we can just print out our thing. 10010 in base 2 is 18 in base 10. Okay, then we have our solution there. So I'll put that up. 3 question 10. Okay, and then you should be able to access that on here now. So there, no? There it is. Okay, so moving on to question 11, the pi one. So in this one, we have to compute pi using this formula, and we have to count how many terms of this, which this is one term, and then this is another term, and this is another term. So we have to count how many terms it takes until before we get 3.14. So use a tolerance of 0.001. So we have to constantly compute pi and test the difference between 3.14 and this, and count how many terms it takes until we can get within this error. So let's start by programming this out. So I will go, oops, this one, I'll save as question 3, lab 3, question 11. And then let me start with get rid of this. Over here, I will change this to question 11 and run that. And yeah, so it's doing nothing because it's printing out nothing. And then let's start with looking at this formula. So we can see that this is kind of 4 divided by 1, and this is 4 divided by 3, this is 4 divided by 5, this is 4 over 7, that's 4 over 9. So this 4 on top is kept constant. This 1, 3, 5, 7, 9, and 11 is all the odd numbers, so it's changing by 2 each time. And this one, you can think of this as just 4, or you can think of it as 4 over 1. So 4 over 1 would just, of course, be 4. So that's why it's sort of easier to put it into that context when you're thinking about this. So let's create a loop first. So start with I, and then have I at 0, I less than 10. And then let's just try and compute 10 of these, or any number you want. So of course we have our numerator, which will be set to 4. We have our denominator, which is always changing. So let's set the denominator to 1 at the start, and at each stage let's add 2. So at each stage we can put the, let's add 2. So we can put the adding 2 down here, but we can also use our for loop, which is pretty powerful to do things. At each stage we're doing this, right? So we can put a comma there and then say d plus equal 2 at each stage. Okay? So then why don't I print out this, this, divide this, and let's put the numerator and denominator in there. And we can see this is looking something like what we have to do. So you'll notice that also we've got this positive, then negative, then positive, then negative relationship. So here we can, I would probably think about making a variable called sign, which is positive at the start, and then in each iteration sign is equal to sign times -1. So let's put LF times this, and then let's put in sign here to make sure we're getting it right. So we've got positive, and then we've got negative, and then we've got positive, then we've got negative. So that looks right. That looks basically what we're trying to do. So let's take a variable that is our pi. So our pi, and set it to 0 at the start. Okay. So then let's put our pi equals plus equal, and then let's put in this formula. So sign times n divide d. Okay. And at each stage, let's print out our pi. Pi equals. And I'm just going to get rid of this so we can just look at this one in our loop. So if we watch this, we can see it's slowly getting towards 3.14. If I put 20 here, then it's getting even closer as we go down. So then the question actually is asking, we need to count how many times it takes until the difference between 3.14 and our computed pi is less than or equal to 0.001. So let's compute down here. I might do it down here. If this absolute function gets the floating point, so that's what the f is there, floating absolute value, So let's get our pi minus 3.14. If this is less than or equal to 0.001, then let's break out of this loop, okay? Then we can say printf it took, and then we've got I, which of course we're counting out, our I many times to compute 3.14. Then we could say with this accuracy, but I'm just going to leave that out. So it took 20 times, and of course it's 20 because we're limiting it to 20. So let's just get rid of this. And it took 385 times. So on this, the answer is meant to be 386. So let's say we are starting I at 1. So that would mean that this is the first time, I guess. And then, is that right? Oh yes, because I should have left that in. Then it took 386 times, which is the correct answer apparently. So let's leave this, and then just printing out this, and that's what we get. Also, since we're using the for loop, we can also use the power of the condition up here. So we can continue, let's, instead of breaking when that condition occurs, let's continue whilst this this condition is still true. So let me try and make this on one line. There we go. Don't need that really. Okay, so then we can get rid of this. And we've got our working solution. Let's go put that back to 0, so then it's the right number, back to 386. Okay, so yeah, there's that one. Then let's go to lab 4, question 4, the perfect number one. So in lab 4, question 4, we've got this, an integer is said to be perfect number if its factors, including 1 but not the number itself, sums to the number. So for example, 6 has factors 1, 2, 3, and 6, but we're not including the number itself. So 1 plus 2 plus 3 is equal to 6. And we have to write a program a function that prints out all perfect numbers between 1 and 1,000. So let's start, let's try it here first. Save this as lab 4, question 4. Okay. And then let's get rid of this. Over here, let's do lab 4, question 4. Okay. So let's first write a function that tests if a number is perfect. Okay. So it returns an int where the int will be 1 if it's perfect, or 0 if it's not perfect. So let's call this is perfect. And of course it takes in an integer. So returns 1 if n is perfect, else returns 0. And then I'm just going to leave the prototype up here, and I'm going to put the function actually below, just for a change. Okay, so here what I'm going to do is I'm going to start at 1, and I'm going to go through every number lower than 6 and just test if it's a factor. I mean, test if those numbers are a factor first. So let's call is perfect with 6, which we know is perfect, and then actually let's put here 6 is perfect is this, And then let's do the same for 7. Because we know that 7 shouldn't be perfect, I guess. Okay, so it's just returning random numbers because at the moment we're not doing anything here. So first let's go through all the factors of n. So start at 1, since we do have to start at 1. So let's have for loop I equal 1, I is less than n, and plus plus. And of course we know that I would be a factor of n if it divides in evenly. So in other words, if n divide I has no remainder, okay? Which in that case we can just do if n mod I is 0. So if the remainder of n divided by I is 0. Then let's just print this out. I is a factor of this. I is a factor of n. So these are the factors of 6, 1, 2, and 3, and these are the factors of 7, 1 and 7. So then let's create a sum. Sum equals 0 at the start. Instead of printing out that factor, I'm going to add it. Sum equals sum plus I. At the end, if sum equals n, then we can return 1. Otherwise, I can return 0. So you can do it that way if you like to think about it like that. The easier way, but maybe it's more tricky for you, is to just think about return if that sum is equal to n. And then that way it's returning 1 if it's true, otherwise returning 0. So let's print this out. So 6 is perfect, that's 1, 7 is perfect, that's 0. So we have a function now, a basic function that checks if that number is perfect. Let's just go through all the numbers then. And also the question asks to make a function to do that. So I don't know, let's just call void check numbers. And just for fun, let's just go put a from and a to here. So check numbers from to 2 to 2 and print if they are perfect. So let's get this, and now we can put this anywhere as long as it's below this. So just for no reason, let's just put it here, but we can also put it here or under is perfect. It's up to you. Then let's have a for loop that goes from whilst from is less than or equal to 2 from plus plus. And then let's just say this is perfect from, and we want to say that if it actually is perfect. So if is perfect from, then print out that that is perfect. Then of course we're doing nothing here, so let's say check numbers from 0, 1 to 1000. So 6 is perfect, 28 is perfect, 496 is perfect. Okay, so that is that one done. Let's try and do question 8. So question 8 is the Goldbach conjecture says that every integer n that is greater than 2 has the property that it is the sum of 2 prime numbers. Using your solution from question 3, write a program that will prove that the conjecture is true for all even numbers between 2 numbers that you will input into the program. So you put in these numbers and it checks for all the even numbers between these two that it actually is possible to, this even number can be created by the sum of 2 different prime numbers. So Let's go and create this file. And actually, I think that we just did. We did is prime. So is prime. Last time we had this to check if a number is prime. So let me close this and say get it, and open up this one which we did before. Is prime. So this checks if n is prime by assuming that it's prime and then going from the number 2 all the way to less than n, and checking if n mod 2 is 0, in which case that would mean that I divides into n evenly, and then we would say it's not prime, break, and then that gives us the answer. Otherwise we assume at the start it is prime. So the only way it's not prime is if we discover that it has a factor between 2 and n minus 1. So let's use this, and I'll save it as question 4, or lab 4 question 8, and I'm going to grab this and I'm going to stick it in a function called is prime, where it takes n and this returns 1 if n is prime, else 0. Just going to copy paste that, don't need the n. Then instead of this I'm just gonna say return 0, since it wouldn't be prime in that case. And I don't need this too. And then after this, if I didn't already return 0, then it must be prime, so return 1. So let me first check if is prime 7 puts is prime. So in this case, let's run question 8. So we know 7 is prime, and if we put 8, it shouldn't be prime, so printing nothing. So that appears to work. So then, let's make a function that takes in an integer and checks whether it is the sum of 2 primes, and let's print out those primes. Okay, so would print if sum is made of primes. I guess let's call it that. And let's put an n as input, and then so we should be going up through numbers starting from 2, because 1 isn't classified as a prime, and let's go to from 2 to less than that number. Okay, so let's have a for loop for I equal 2, I is less than n. And let's just printf that I for now. I. And then let's just copy this and test it with a couple of numbers. So let's put this in here, and let's test with 4 and 8. Okay, 4 and 8. Okay, so 4 would be looking at these numbers, 8 is looking at these numbers. We can see that this one is 2 and 2, so 2 is there, and this one we can see that 3 and 5 is in this list, so 3 and 5. So let's then check to make sure that I is prime. So let's not even do this unless we're considering if is prime I, then we'll print this. Okay. So for 2, we've still got our 2 there, and for 8, we've got our 3 and our 5. So if it's prime, then we know we want to check if I plus x is equal to n, where I and x are prime. Okay. So if and we know also that variable x, if we just followed this, then we can put we know that if we subtract I from both sides, so subtract I here, then it becomes positive x equals n minus I. Okay, which positive x is just x, so x is n minus I. So let's compute x then. X equals n minus I. Then we can say if we already know the I is prime, so if is prime, x is prime, then let's do 2 things. Let's first say printf n is equal to let's say this is equal to this plus this, which looks like this, I guess. And we'll put a new line character here. We'll put n. Here we'll put I, and here we'll put x. And then after that, we already discovered that it was true, so let's return 1. Let's just return straight away, because we're printing here. If that turns out to not ever return there, then let's print out here not true for I. So that means that we proved it false. Okay. So let's try that. So 4 equals 2 plus 2, 8 is 3 plus 5, so that appears to be the answer for this. So let's go ahead and create our function that you input the number range and you test all those numbers between that range. Okay. So let's just call this test, and from and to, and here let's call test with 4 and 10, and then 40 and 50. So test with 4 and 10, and then test with 40 and 50. Okay, so here let's create a variable I and say for I equals from I is less than or equal to 2, I plus plus. And now, so let's print out testing I, and let's just print out that. So this is the test for 4 to 10, this is the test for 40 to 50, so it looks like we're testing the right numbers. But remember, we just want to be testing all the even integers. So then let's say if 2 goes into that evenly, then that means it must be an even number, then test. So we're just testing with 4, 6, 8, and 10. 4, 6, 8, 10. And this one's 40, 42, 44, 46, 48, and 50. So those are those numbers there. Okay, so instead of doing this, let's use this function that we built before and we checked it a bit. Put in I there. Run that. And then we've got these, which these look to be like the right answers. 3 plus 7, 3 plus 7, 46 is 3 plus 43, 46 is 3 plus 43. That looks right. So yeah, let's leave it at that then and go on to question 10. So I'll put these up. And 11 from lab 3 and questions 4 and 8 from lab 4. Okay, so yes, so we converted binary to decimal, and we did the pi one, we did the perfect number, we did Goldbach conjecture. So let's test out decimal to binary one now. Okay, so let's save this as question 10. Okay. And then let's clean up some of this. Okay, so this time we have a decimal number that we want to convert to the binary equivalent. So there is an algorithm for this, and let's say create a function called bind to decimal and put in the decimal number. So at the start we'll just return 0. Down here we'll say printf this in base 2 is this in base 10. Let's put test as 15 at first. 15. Test, and let's put bin to des of test in here to test. Then let's run this. Question 10, I think it is. Yes. So 15 and base 2 is blah 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 and base 10. So we haven't got this working yet. So basically the algorithm, what it does is we're going to first whilst d is more than or equal to 0, more than 0 actually, I should say, what we're going to do is compute d mod 2. So that tests if d is even. If it is, if in the case of a binary number, we know that, for example, 9 in binary, if we mod it by 2, we're actually getting the rightmost digit, right? Because remember, in base 10, if we have this number and we mod it by 10, then it would equal 4 because it's getting this one. If we mod this by 2, then we equal, we're equaling 1 in this case. If we have, for example, 6, then this would equal 2. Okay, so that's the basic concept here. So let's start with that. Let's say we know the answer here is 1111. So let's put d is d mod 2 and print this out here, I and d there. So we can see that's 1. So the rightmost digit is 1 here. So then, in order to shift down when the number is binary, we're dividing by 2, right? So let's say I have the number 8 in binary, and I divide that by 2, okay? If I do that, then obviously the answer, 8 divided by 2, and then this is in binary. 8 divided by 2 is 4, which 4 is this in binary. So effectively dividing by 2 shifts the bits down. So if I have 10 in binary, divide 2 equals, of course we know that the answer 10 divided by 2 is 5, which in binary 5 looks like this. So we've essentially shift this 1 here, shift this 0 here, shift this 1 here. So that's why the answer comes out. So let me clean up this. And let's do this. So whilst d is above 0, let's compute d. And let's print out this value d. And then for our d, let's go divide equal to shift it down at each stage. Error, undeclared D. D is right there though. D. Okay. Oh, it's for this D. It's for that D down there. Okay, that's okay. So, let's do this. So 1, 1, 1, 1. And we'll notice that that is our answer. 1, 1, 1, 1. 1, 1, 1, 1, yeah. So what about for 27? Let's test. So for 27, we know that the answer is 1, 1, 0, 1, 1. That would be 1, 1, 0, 1, 1. So let's test with, actually a better one is 10. Let's test with 12, okay? So we know that 12 should be 1, 1, 0, 0, okay? Because it's 8 plus 4 is 12. So let's do this. So 1, 1, 0, 0 is 1, 1, 0, 0. But we can see that this is actually backwards. So it's backwards from what we want to have. So let's have an output. So bin into decimal. And actually this should have been called, sorry, decimal to bin, I just noticed. That's why I was getting confused. Okay, so let's have an output which is our binary number. Okay? Set that as 0. Okay. And also we need to change this around too. Okay, so we have our number, but it's backwards. So let's try putting it into B and then shifting B up by 10 each time. So let's set B equals B times 10 plus D. Okay, so that way we're first shifting B up by 10 and then we're adding D. Okay, and then let's here return B. 12 in base 2 is 1, 1 in base 10. B time equal 10. And B plus equals D. No. Okay. So we should be getting 1, 1, 0, 0. In this case, let's start from the start. So I can see that B won't be shifted up in this case if B is 10 already. Let's print out B at each step. So let's go printf B and then printf B. Yeah. So B was this. Let's say B equal so B equals 0 because 0, B is 0, B is 0, B is 0, B is 0. B is, let's put this. So after the first digit, which would be a 0, then after the second digit, then after the third, B shift by 1, 0, 1, 1. Ah, yes. So the problem with this is that we're putting B in backwards by shifting the first number, the rightmost digit in, and then shifting it up. So what we need to do instead of putting it in backwards is put it in forwards. So let's try a different strategy where we put in I equals let's put in 1, 2s, 4s, and this one, I is 4. And then let's add in the digits. So B equals power of 10 to the power of I times D. And then let's put I minus minus here. And then let's check out B at the end. Yes. Include math.h here, so we can use the power. 10 to the power of I, and then I minus minus. Should be right. 12 in base 2, 10 in base 10. Let's print out, B plus equal this. Okay. 1, 1. So this is this, then it's right. Okay, so then we need to find out how many digits this would be in binary. So we can do that by going log of D, which is the input, divide the log of 2. Okay, so then we can just add 2 to that, and then that in base 12 is that. Let's test for 15. So 15 should be 1, 1, 1, 1. Which should be this then. Let's start I at 0 actually, and then increase I by 1 each time. Okay, so I think that I should have done this first, sorry. So this is my thinking. So I start with the binary, this will be my output, and I set it to 0. And then I set I to 0, so I is increasing at each stage. I is increasing each stage, and each time I add to the binary output 10 to the power of I multiplied by D. So I get the right spot, so it would first of course start off in the 1s, which are 10 to the power of 0 is 1, and then the 10s, which of course 10 to the power of 2, 10 to the power of 1 is 10, so that's the 10s, and then hundreds, etc., and keep going up for as long as I need to. So then we have our function that finally works. So let's test that with some other numbers. So test with 27, and we get 11011. So 11011. Then we should be able to test with any other number. So if we get calculator and put it in programming, which already actually and we select decimal and we go a random number like 569 or something, then we can see 569 in binary should be this number here, 1000111001. So let's check that. What number did we put in? 569. 569. Okay, 1 and 3 zeros. So let's check this. 1 and then 1, 2, 3 zeros, and then 1, 1, 1. So after the 3 zeros, 1, 1, 1, and then 0, 0, 1. So then 0, 0, 1. And there we go. That's to convert decimal to binary. And that's all the things that we went through. So I will save this. And put it up. And now, voila, you have all of these examples to look at for later as well. So, yes. I was going to add one more thing that I think I didn't see it covered, maybe in the lecture on arrays. So let me just call this one array test.c and get rid of some of this. And this one, let me run this array test.c. And that was when creating arrays. So let's create this array which has 3 values in it, and 3, 4, and 6, and let's create a function called print array. So void print array. Let's put in the array here and then put in the length of the array here. Over here, let's create a loop, I, and let's go for I equals 0, I less than L, I plus plus. And let's print out that version of the array, that value in the array, sorry, array I. If I is less than L minus 1, then at the end of that, let's print out the comma. And then here, let's print out this and a new line, I guess. And here, let's print out the upside. Okay, and then let's try this function, print array A, and then it has a length of 3. So yeah, that's printing A. Then let's have a regular integer, int B equals 3, okay, and printing that. Okay, so when we have some function, void modify, and we input an integer, x, and I say x equals x plus 2, plus 2000, let's just put. If I have that function and I have b and I print out b here, and then I pass in modify and I pass in b here, oops, and I modify b and then I print it out. In this case, because we're passing in b's value, this is separate from b, so that actually creates a new copy of x and places the value of b inside x. And when I modify x, it doesn't change b on the outside. So that's why b remains a value of 3. If I have another modify function, and I use it with an array X, and I put in some index that I want to change, and I say X index equals X index plus 2000, like that. That value will be changed. So once we print the array, let's say modify X, modify A, index, let's put 1 here, so modify the 4. And then let's call print array again, A, and it's got 3. In this case, it's complaining that I'm not using the more modern version of GCC, C99, which I can put to use the up-to-date version, where I think I can use 2 functions that have the same name as long as they have different amounts of parameters and different types. So still, let's call this modify array then. Still complaining. Okay, so you'll notice that whereas modify for integers or other numbers or other data types such as double and char don't change the value, for arrays it does, and the reason is that we're actually passing the memory reference to the first piece of data in the array. So that's what's causing this to change. So whenever you pass in arrays like this, then you're actually passing in the same array. So you're actually passing in A there. When you do it for integers, it's actually passing in the value. So I just wanted to go through that. Okay, thank you.